Thank you. Hi, everybody. So I am from Norway. This is University of Stavanger in Norway. I arrived here in Korea yesterday. It is now 3 o'clock in the morning in Norway. That means that my body thinks that it's 3 o'clock in the morning. And I have never tried to give a lecture ever at 3 o'clock in the morning. So if I fall over on the stage, or lose my train of thought, or say something that's complete nonsense, blame it on the jet lag. So I used to, many years ago, I lived in Korea, and this is my Korean name. I have my Korean name. Okay, so as Kung-won said in his opening remarks, where we are today, 2020, last 5 years, is a new golden era in gravitational physics. And that is in large part because of the detection of gravitational waves by the LIGO collaboration in 2015. They won the Nobel Prize in 2017 already, and this is now changing a lot of the things that we are now able to use these detections to do a lot of astrophysics and also test a lot of fundamental physics with. And the first detection was made in 2015 on the 14th of September. It was announced to the world, so it was processed by the collaboration for 6 months. It was announced to the world on the 11th of February 2016. That means tomorrow it is 4 years since it was announced to the world. And when it was announced to the world, I remember well, there was a big press conference in the United States. We had a big press conference. I was in Germany at the time. We had a big press conference at my institute. There were politicians there. There were translators. It's the only ever time in my life that I've been to a scientific meeting where there has been simultaneous translation of what people are saying from one language into another. Everybody with little headsets on listening to the translators in the translator booth, translating on the TV. I was in the newspaper. It was all very exciting. It was the most exciting day of my scientific career. And that was the 11th of February 2016. On the 8th of February 2016, my daughter was born. That was the most exciting day of my life. So in the same week, I had the most exciting day of my life and the most exciting day of my scientific career in the same week. That was quite a week. 4 years ago this week. Okay, and we had a big press conference in Germany. It was a big press conference in United States. There was also a big press conference here in Korea at the very prestigious Ibis Ambassador Hotel in Seoul. Many of these people are people in the Korean gravitational wave community. You might recognize some of them in this room. Some of them also live here in Daejeon but are not here currently. This guy here, he also wrote this book about gravitational waves. So you will see wherever you buy good books, you will be able to find this book all about gravitational waves as well. So all over the world we had a big press announcement. It was very exciting. We were on the front page of all the newspapers. The last time that I was in Korea, 2017, 3 years ago, I was here in Daejeon for a meeting. That was the week when the first merger of 2 neutron stars was announced. This is the most studied transient event in the history of astronomy. Every single astronomer who has a telescope has pointed it at some point to that part of the sky where that binary neutron star event happened. And I remember that we went all around everywhere in Daejeon trying to find a newspaper that had an article about that event. And we had to go all around this city, the whole city of Daejeon, until we found one place here in Daejeon that had a copy of a newspaper that on page 6 or something had an article about it. So from the first event in 2016, which was front page news everywhere in the world, to the BNS, which in some ways is more important, somehow became page 6 on some newspaper somewhere in Daejeon. So that was a lot of fun. It was also in the newspaper in Norway. This is just to show that it was also in Norway. Sorry, my slides will be in many different languages today, so you'll just have to survive. For those of you who don't speak Norwegian, this says that researchers have found proof of Einstein's theory, and it is difficult to find words that are big enough to describe this. So this was a quote from one of the scientists in Norway when they was asked by the journalists, how would you describe this detection of gravitational waves by LIGO? He said it's difficult to find words to describe how big this is. This is so big in science and in history of science, it's difficult to find words. And that's probably a little bit of an exaggeration, just as Kungwon's two periods of great advance was also a little bit of an exaggeration. But that's how it was. It was really quite an exciting time. Okay, so what I'm going to talk about in my lectures are 3 different things. I'm going to do something slightly different from what Jan did, so I'm not going to write down formulas for you and develop theory from the ground up. We are going to talk about some theory. I am going to tell you something. Most of it's going to be slides. You are welcome to take notes if you want. I assume that if everything's getting broadcast on YouTube, the lectures will always be on YouTube for you to rewind and see again, right? It's not just being streamed. It's actually just there forever now, right? Yes, probably. Probably there forever. Though the PDF file is there forever anyway. So you can take notes if you want, or you can just follow along as you wish. So I'm going to talk about the theoretical background of gravitational waves. So the detection of gravitational waves that I've been talking about in 2016, this was the culmination of 100 years of theorists arguing about gravitational waves, whether they were a real thing or not, whether they were really produced in our universe, whether they were really predictions of Einstein's theory, whether anybody was going to see them, all that sort of stuff. That was the culmination of all that theoretical arguing, so we'll talk a little bit about that. I will say something about how we know that we are seeing gravitational waves, so you cannot actually see gravitational waves with your eyes. This is one of the big points about gravitational waves. We have now a new way of learning about the universe that doesn't require photons, doesn't require our eyes. So you cannot see them. So how do we know that we actually are seeing something or actually are detecting something? And then probably in the second lecture, which is on Wednesday probably, I will talk about what we can use gravitational waves for, both the astrophysics and also the fundamental physics that we can do with gravitational waves. So that's the main plan. So gravitational waves, they are a prediction of Einstein's theory of general relativity. Now that does not mean the same thing as saying that Einstein himself predicted gravitational waves. In his career, after he came up with his theory of general relativity in 1916, which is probably also one of the most important epochs in the history of general relativity, don't you think? When Einstein actually came up with, I think there are 3 important periods at least. No? There's 1916 as well. So when Einstein came up with the theory of general relativity, his theory of general relativity, the fascinating thing about it is, I don't think he really understood his theory. And if you know something about Einstein's career after he came up with the theory in 1916, you know that in the years that followed, he spent a lot of time trying to understand what exactly were the predictions of this theory of his. And you may know that he predicted, for example, that the universe had to be static. He didn't believe that the universe was expanding. He therefore predicted this thing called the cosmological constant, which he then described as his greatest ever blunder. He also wrote a paper in 1939 saying there are no such thing as black holes. And actually what this slide shows is he changed his mind many times, even after he came up with his theory, about whether the theory actually predicted gravitational waves. So this is now in German, so we've now switched from Korean to Norwegian to German. Now it's now in German, or parts of it in German. So in 1916 he was writing to Karl Schwarzschild, who is the guy who came up with the Schwarzschild solution, and he told him that there are no gravitational waves which are analogous to light waves, right? So he had taken his theory, he had tried to work out, he knew that in electromagnetism predicted electromagnetic waves, so it was obvious to ask, does my field theory of gravity predict gravitational waves? And he looked to see if the same thing that happens in electromagnetism happens in gravitation, and it turns out it doesn't. So he then concluded, okay, in that case there are no gravitational waves. And what this means is that he realized that if you have a changing dipole of charge, which in electromagnetism, if you have a charge and you wiggle it up and down, it will emit electromagnetic waves and you will get light coming out of it. And he realized that if you have a changing dipole in gravity, this will emit no gravitational waves. So he decided that there were no gravitational waves in his theory. But then, very shortly after, in 1916, he then wrote an article that he then found out that actually, if you go to the next order, so you don't have a changing dipole, but you have a changing quadrupole of your mass distribution, then that will emit gravitational waves. So he wrote a paper which is often taken as his first prediction of gravitational waves, where he worked out the theory of this, made a bunch of mistakes, calculated some things that weren't true, predicted different modes of gravitational waves that don't exist, and most importantly, he wrote that if you try to work out how much energy is given by gravitational waves, you will find that for all reasonable systems in the universe, that the amount of energy that is given out by gravitational waves is always tiny, inconsiderable. It's absolutely negligible, so it will have no actual consequences of interest whatsoever. This is what he thought in 1916. He didn't know in 1916 of the existence of black holes and neutron stars, and it was only when people realized that there are such things as black holes and neutron stars that you can have lots and lots of mass compacted into very, very small places, and then you can move these masses around each other very, very quickly, that you can actually produce huge amounts of energy in gravitational waves. So he thought this was going to have no practical consequences in 1916. In 1918, after Eddington had made fun of him and his arguments that some of his gravitational waves that he predicted in 1916 were pure gauge effects, they were just an effect of the way that he decided to write his equations, and Eddington showed that the gravitational waves that Einstein had predicted in 1916 could travel at any speed you like, including infinity. And this had made Eddington say that they move with the speed of thought, because they are just pure imagination of Einstein's imagination. In 1918, he came back to the issue and said, okay, I made a mistake in 1916. He actually made several mistakes in 1916. So he had to come back and address it again. That was all very good. But Einstein had used an approximation to his equations, because his equations are nonlinear differential equations, and he knew that it was basically impossible to find exact solutions to his nonlinear equations. So he'd use an approximation called a linearization approximation to make the equations easier to solve. And he knew that this approximation was only an approximation and had no way of checking whether it was a good approximation or not. So he spent the next 20 years almost trying to find an exact nonlinear solution to his equations that had gravitational waves in them. And he decided in 1936, after working together with Nathan Rosen, together with a young collaborator, I arrived at the interesting result that gravitational waves do not exist. Do not exist. He had proved, at least to himself, that they did not exist, though they have been assumed a certainty to first approximation. So this means that by making an approximation to his equations, this linearization approximation, you were able to make something that looked like a wave equation and something that looked like gravitational wave. If you go and look for a nonlinear solution, a full solution, a proper solution of his equations, he had decided that they didn't exist, that this wasn't possible. And he wrote a paper about this together with Nathan Rosen, sent it off to the journal, and the journal sent it to a referee, and the referee said, this is wrong, Einstein is wrong, he is mistaking coordinate singularities for true singularities, he's making mistakes, he doesn't understand his own theory. Einstein does not understand general relativity. This happens repeatedly throughout Einstein's career, that he doesn't understand his own theories. It's not easy, general relativity. Even Einstein didn't understand it. So then it was a little bit of backwards and forwards with the journal and the referee. And eventually Einstein was maybe led to think, well, yeah, maybe my argument wasn't so strong and I cannot say definitively there are no such thing as gravitational waves. But pretty much the last thing he ever said on the matter at a lecture in 1936 in Princeton, if you ask me whether there are gravitational waves or not, I must answer that I do not know, but it is a highly interesting problem. So that was pretty much the last thing that Einstein ever said on the matter of gravitational waves, having gone through multiple versions of, yes, they exist, no, they don't exist, here is the proof they exist, here is the proof they don't exist, here is the argument why they'll never have any positive effects, all of these things, backwards and forwards. So if we ask ourselves, did Einstein predict gravitational waves? It is not so clear. They are a prediction of his theory, but it took theorists, other people other than Einstein, it took us 50 years, at least 50 years, to work out whether gravitational waves were really a prediction of Einstein's theory of general relativity. Right? There was a lot of arguing about this in the theory community for 50 odd years. So the detection of gravitational waves shows that ultimately the theoretical arguments that said they do exist were correct. So this paper where he supposedly proved that gravitational waves do not exist, at this time he was living in the United States. He'd been thrown out of Germany for political reasons, didn't want to go back. And he sent this letter to the Physical Review, which was the big American physics journal at the time. It is now one of the biggest physics journals. Now they have Physical Review A and Physical Review B and Physical Review D and Physical Review letters and all sorts of things. He sent the paper to the editor. The editor sent it to a referee, which was the standard procedure even in those days, in the 1930s in the United States, to send scientific publications for a referee, to an anonymous referee. The anonymous referee said, this incredibly famous scientist, the most famous physicist of all time, is wrong. You shouldn't publish his article. And the editor of the journal sent this letter to Einstein saying, we're not publishing your article because the referee says it's wrong. And Einstein was very angry about this. And he wrote a very angry letter back to the editor, again it's in German, saying that I sent you the article to be published. I am Albert Einstein. I sent you the article to be published, not to be sent to a referee. The referee is wrong. The referee is wrong anyway, and I'm going to send it somewhere else. And actually, Einstein never published ever again in the Physical Review after this. He was so angry about this. But it just goes to show you that in the 1930s was a time when not only could you complain about journals sending your papers to referees, and referees being arguers, but you could also complain in German to American journal editors. You could write letters in German to American editors and expect them to understand what you were talking about. Not anymore. Right, so that is that. So eventually he, after possibly talking to the anonymous referee who contacted him, he maybe realized that his proof wasn't very good, and he patched it up slightly, changed it a little bit, changed the conclusion, and even changed the conclusion without consulting with his collaborator, Nathan Rosen. Nathan Rosen is the guy who is famous from the EPR paradox. He is the R of EPR, and sent it back to another journal, different journal, to be published, saying, well, maybe there were gravitational waves after all. Nathan Rosen actually never accepted these arguments, and he spent his entire career, even up to the 1980s, writing papers that say there are no such thing as gravitational waves, or whatever they are, they don't carry energy, or whatever they are, they're not caused by binary systems that are gravitationally bound, things like that. So this was a theoretical debate that was held and fought strenuously by people at the time. Is my microphone still on? Yes, it is. Okay, so here is the basic cartoon sketch of why people think there should be gravitational waves. So in Newtonian gravity, the standard theory of gravity that held sway for 250 years when Newton came up with it, what happens is if you have a gravitational field due to, for example, the sun or me standing here, and you move the sun up and down, change the sun, change its position, change its mass, change its distribution of its mass, then that effect is instantaneously felt everywhere in the universe. So if I wiggle up and down the sun over there, I will instantaneously feel its effect, the gravitational field in Newton's theory, I will feel it instantaneously over here and everywhere else in the universe. And Newton knew about this. He knew that this was a property of his theory. And when he proposed his theory, other people also pointed this out. Leibniz, for example, pointed this out and said, this is absurd. This is a crazy way of things to happen. Things cannot propagate instantaneously without any other mechanism of being transported from one place to another. Your theory has to be complete rubbish. This was actually Leibniz's main reason for believing that Newton's theory was complete rubbish. The problem for Leibniz was Newton's theory was so successful, it was so good at explaining so many things, and Newton's attitude to this was, I don't know how this happens, it just happens. Somehow, it just happens. Look, it works really well. It explains all the orbits of all the planets. It explains the tides. It explains all the cannonballs. It explains everything. So I don't know how this happens, but it just does. So deal with it. And this was the basis of Newtonian gravity. This was everybody was eventually happy with this for 250 odd years. So they are, if you look at them mathematically, Newton's equations under a perturbation, they give you what's called an elliptical equation. It's a Poisson equation. It's elliptical in terms of as a differential equation. This means its propagation is instantaneous. So there are no gravitational waves in Newtonian gravity. Gravitational waves are not a prediction of Newtonian gravity. In Einstein gravity, you do the same thing. You wiggle your source of gravity, you wiggle the sun, you wiggle your arms, whatever it is. You have then what are called hyperbolic equations. Hyperbolic equations are things like the wave equation. This means that there are propagations of those perturbations through the field that travel outwards at some finite speed, in this case the speed of light. So in Einstein's theory, because the equations are hyperbolic and not elliptical, there are these gravitational waves. And this means that gravitational waves are a generic prediction of relativity plus gravity. If you take Newtonian gravity and you make it compatible with relativity by requiring that when you change something over here, it takes a finite amount of time for it to get over there, you will always have a theory that predicts at some level gravitational waves. You won't necessarily have Einstein gravity, but you will have a theory that is compatible with special relativity, finite propagation of signals, and with gravity, or the Newtonian limit of gravity. This means whatever theory you come up with, if you require it to be relativistic and compatible with Newtonian gravity in some limit, you will somewhere have gravitational waves. This means it's very difficult to write down a theory that is both relativistic and compatible with Newtonian gravity that does not have gravitational waves in some way or another. Now those gravitational waves might not be the gravitational waves that are predicted by Einstein's theory, but they will be some kind of gravitational waves. So gravitational waves are a generic prediction of relativistic theories of gravity. So this issue of the speed of gravity, this was an issue that people had thought about, that Leibniz had complained about when Newton published his theory of gravity. And actually, people had looked into this and had wondered about this, and had wondered when they figured out that the speed of light was finite, that it was taking a finite amount of time for light to come from Jupiter to Earth or from the Sun to Earth, people immediately thought, well, maybe it also takes a finite amount of time for the gravity to come from Jupiter or from the Sun to Earth. And one of the things that prompted this investigation was in 1693, Edmund Halley, who was a big astronomer in Britain, was looking back at ancient Babylonian and Arabic eclipse observations. People had recorded when there were eclipses that happened thousands of years ago. And he noticed that the period of the moon's orbit seemed to be getting shorter. It seemed to be taking less and less time for the moon to go around the Earth. And someone who looked into this in great mathematical detail was Laplace, who came up with a number of possible explanations for this observation, which didn't fit the simple two-body model of the moon and the Earth. And one of the possibilities looked into was the possibility that the speed of gravity was finite. And if it took a finite amount of time for the gravity to go from the Earth to the moon and from the moon to the Earth, this might affect the observations. And he looked into this in his treatise on celestial mechanics. This is now in French, in volume 4. And he was able, from the stability of the solar system, the fact that the solar system exists, and has seemed to exist for many thousands of years at least, he was able to put a bound on the speed of gravity in Newtonian gravity, or at least as a finite propagation effect in Newtonian gravity, that the speed of gravity should be larger than 7 times 10 to the 6 times the speed of light. So more than 7 million times the speed of light was the experimental bound on the speed of gravity for Laplace, based on Laplace's theory. Right? So he had looked into this, he had taken the data, worked out a theory, and said, here's a result, it's bound to be greater than, if it is finite, it is greater than 7 million times the speed of light. And this is unfortunate for Laplace, because the way the solar system works, in particular the way the sun works, is even though we see the sun as it was 8 minutes ago, it takes 8 minutes for the light to get from the sun to us. Even though we see it as it was 8 minutes ago, the direction of our acceleration towards the sun, right? In order to go around the sun, we have to have an acceleration towards the sun, a centripetal acceleration towards the sun. The direction of that acceleration points to the instantaneous position of the sun relative to the Earth. This is some rather strange feature of the way that the solar system works, that means that by looking at the solar system, it is very difficult to notice that gravity travels at the speed of light. In fact, the solar system, the gravitational dynamics in the solar system, or at least for the Earth going around the sun, are such that it seems as if gravity is instantaneous. So this Newtonian theory that said gravity is instantaneous, it actually is a very good model for the way that gravity works in the solar system. Yeah, because the solar system actually does act as if gravity is instantaneous. Right? And this is a little bit similar to the way that things work in electromagnetism with the Coulomb potential, and the way that the Coulomb potential works when you have an electron, for example, going around a hydrogen atom. If you look at the relativistic corrections to that, you find that the relativistic corrections are actually cancelling at leading order. There's actually a magical cancellation that means that the acceleration is always instantaneously to the instantaneous position of the source. Now, if the solar system had been composed of 2 stars that were roughly of the same size, it would have been obvious even to Laplace that gravity was traveling at the speed of light. But because the solar system is composed of one big object, the sun, and a lot of little objects that go around it, it's not obvious at all. Gravity acts in the solar system as if it's instantaneous. So it was bad luck for Laplace. They would have discovered the finite speed of gravity hundreds of years before Einstein if the solar system had been slightly different. Next one.
Remember the speed of light was known?
Yes. The speed of light was known at least to a factor 2. So Ole Rømer, Danish astronomer, had noticed from looking at the periods of the moons of Jupiter that the periods of the moons of Jupiter was not constant. And from that he was able to work out that actually it's taking light some amount of time to come from Jupiter to Earth.
It was before this?
Yes, before this. Yeah. Yeah, certainly before Laplace, probably after Halley. It was between these two, I think. 1720s, something like that. Yeah. Ole Rømer. So they knew that they knew that the speed of light was finite. They knew it was taking a finite amount of time for the light to travel. So they knew this number. This C number was known reasonably well. Yep. Okay. So that was what we knew up until Einstein. The experimental data was consistent with an infinite speed of light. And now comes Einstein, and his paper, which is his title now in German, Näherungsweise Integration der Feldgleichung der Gravitation. And this was the paper that he wrote in 1916 that predicted gravitational waves for the first time. And I stole from one of Kung-Won's paper the Korean translation for this. No? Checks out in Google, so it must be right. Yeah. So this is the approximate integration of the field equations of gravitation, right? So Einstein knew that his nonlinear equations were basically impossible to solve exactly, so he wanted to use approximations to solve them. So this is one of the first times he tried to use approximations to solve them. So what is the argument? These are the Einstein equations, right? GAB, this is the curvature, the space-time curvature. This is the energy momentum tensor. Very, very difficult to solve. Series of coupled nonlinear differential equations, complete nightmare to solve. So what Einstein did was he took a small linear perturbation. So this is the metric. If you split the metric into the flat space part, the bit of Minkowski space, and a small little perturbation, this HAB, and then you put that into the Einstein equations, and every time that you see h times h squared, or h times the derivative of h, or anything that has h, two times h in it, you throw that away, you put that to 0. So you're linearizing the nonlinearities. You're throwing away all the nonlinearities by just linearizing the equations. If you do that and you work for it consistently, and you put the TAB equal to 0, what you will end up with is an equation for these h's, for these perturbations, that looks like this, that describes a wave equation. So what it means is, if you have a small perturbation to flat space-time, you have some small perturbation to your gravitational field, if it stays in the linear regime, happily stays in the linear regime, it will propagate, that perturbation will propagate from over here to over here at the speed of light described by this wave equation. Right? This you can show by linearizing the Einstein equations. And not only that, but you can also work out how to produce such a perturbation. Right? So if you have some mass and you want to somehow produce that perturbation in your gravitational field, you can also work out how to do that using this linearization procedure, using this thing here, which is the quadrupole tensor for the distribution of energy or mass. This is the mass density, the three-dimensional mass density, with its position, xi, xj, these are positions. This is the delta ij, the thing that's 1 or 0, depending on whether these are equal or not. This is r squared, the distance to the mass. You integrate this over the volume, over some region of space. Doesn't have to be where the mass is. It can be outside where the mass is, away from the mass as well. But you will get this quadrupole tensor that describes the distribution of your mass in your space. And Einstein was able to show that this perturbation here, this small perturbation here, takes this form here. It is a second derivative, a second time derivative of this quadrupole term. So this quadrupole term will be non-zero if your matter distribution is in some way lumpy. If you just have your matter distributed in a sphere, perfect sphere, then your quadrupole will be 0. But if your sphere has bumps on it for some reason, then your quadrupole will be non-zero. And if those bumps change in time for any reason, because it rotates or something, then this second derivative will be non-zero. And if this second derivative is non-zero, you will start producing these perturbations, and then these perturbations will be taken by the gravitational field and propagated at the speed of light. These are the gravitational waves. Right? So that is what gravitational waves are at the level of the linearized Einstein equation. So this is the argument that Einstein had in 1916 for why he initially thought there were gravitational waves. Right? And nowadays, every student who writes a PhD thesis in gravitational wave physics, when they write in the introduction to their thesis, what is a gravitational wave, this is the argument that they write. All of them. Every single one that does this. Right? They all copy each other and they write like this. Right? Einstein knew that this is not reliable, right? Because this relies on an approximation. It relies on your ability to do this split, and then when you put that into the equations, to throw away, to ignore all the terms that are quadratic in this perturbation. Right? And this is one of the problems of nonlinear theories, is there is no way really to know what a nonlinear theory predicts by linearizing that theory. You cannot do that. That does not work. Right? You can argue all you like that that perturbation is small, 10 to the minus 30, 10 to the minus 50, whatever you like, but there is always the possibility that nonlinear effects will blow that perturbation up to some large value somewhere, and your approximation will not be valid. Einstein knew this, which is why Einstein spent the next 20 years trying to find a nonlinear version of what is a gravitational wave. Right? So even though every student who writes a PhD thesis in gravitational waves writes this as what gravitational waves are, even in Einstein's time, Einstein knew that this is not the right answer. This is a way of thinking about the answer, but it is not a robust, reliable way of thinking about what a gravitational wave is. This thing here, which if I had submitted the PowerPoint instead of the PDF would have been moving, this shows the effects of a gravitational wave on a circle of masses, test masses. As the gravitational wave moves, what it does is it will squash a circle first in one way, and then in the other way, and then in the way again, and basically the test masses will oscillate upward, up and down, and in and out like this with time. So if I'd submitted the GIF instead of the PDF, this would have moved. That's the way it is. Right. Now, there is one conceptual thing that is important and misunderstood by a lot of people about what are gravitational waves. This is because gravity fundamentally is a tidal interaction. You notice the effects of gravity from the tidal forces. You take two masses and you see how gravity moves those two masses relative to each other. And when we say that we are detecting gravitational waves from binary black holes that are hundreds of millions of light years away, what that does not mean, it does not mean that we are feeling the effect of their gravity changing because they're basically changing their position on the sky, and effectively the Newtonian potential of those black holes is somehow changing the gravity here on Earth in a meaningful way, right? Because the tidal force due to this Newtonian part of the potential that also exists in the Einstein's theory, this tidal term due to the Newtonian potential, this falls off as the cube of the distance. right? It's falling off as you get further and further away. These black holes that we see, hundreds of millions of light years away, we do not feel the change of the Newtonian part of their potential. That's not what we feel. What we feel is the tidal force due to the propagating gravitational waves, not just the fact that they're changing the gravitational field, but they're actually putting gravitational waves into the field, because this only falls off as 1 over the distance. Right? So if you are very, very close to these black holes, standing in their solar system, for example, you will feel this much more than this, right? Because at small distances, at small r, this will dominate over this. But if you are a long way away from those black holes, you will feel this more than you feel this, right? So these are two slightly different things, and they are acting in slightly different ways. Okay, so here is now the first example of what a true gravitational wave is in the full nonlinear glory of Einstein's theory. Right? These are what are known as PP waves in Brinkmann coordinates. So this is a metric element, describes a four-dimensional metric with some functions. There are coordinates u, v, x, and y, and there is this function here h. Right? This was already known in the 1920s, and this thing here, if you plug it into Einstein's equations and you don't throw away any of the terms, you keep all terms, keep the whole thing, this will be a solution of the vacuum Einstein equations, so TAB equals 0, if and only if this h takes this form here. Right? So these are now these coordinates, x and y here, x and y here, and there are two free functions here, this a of u and b of u. And those two free functions can be anything you like. Whatever your favorite function is, you can put that in for a, put that in for b, whatever you like, you can put in a and b, and it will be a solution. This thing, all of this will be a solution of the vacuum Einstein equations. Right? And these will be true gravitational waves in a true nonlinear sense. This is what Einstein was looking for. These two free functions here, these two free functions correspond to the fact that gravitational waves have two propagating modes, two independent polarizations that tell you information about that gravitational wave. These are the two free functions, there are two polarization states of this gravitational wave, it's A and the B here. So this is a fully general plane wave propagating in some light-like direction with some transverse directions x and y. So it's like a plane that just travels across the universe like a plane with two degrees of freedom, A and B. Right? This solution, this thing here, this is not flat. It is not Minkowski space written in some funny coordinate system. It is a truly non-flat curved solution of Einstein equations. It has a non-zero Riemann tensor, but all of the contractions of the Riemann tensor, so every scalar contraction that you can make of the Riemann tensor vanishes. So even though the Riemann tensor itself is not zero, every contraction that you make with the Riemann tensor is zero. This has some rather interesting special properties, this solution here. And that fact that all of these contractions of the Riemann tensor also vanish means that actually this PP waves in Brinkmann coordinates are not only a solution of Einstein's equations of gravity, they'll actually be a solution of any equations of gravity if you have, for example, an F of R or a theory with higher order derivative corrections to gravity, to Einstein's theory. If you have some quadratic, you have some Gauss-Bonnet terms, or you have other terms that you add in, this thing will also be a solution. This is showing you that gravitational waves are a very, very generic prediction of relativistic theories of gravity. So that's nice. It's an exact solution. It describes an infinitely large plane that propagates. It's everywhere in the universe. It propagates as a big sort of wall moving across the universe. It's difficult to relate it to actual sources. It's difficult to see how this is truly produced by, for example, two black holes going around each other. It's difficult to relate this to exactly what you would measure with an actual detector. But this is an actual nonlinear full solution of Einstein's theory.
But somehow that's unrealistic.
It's unrealistic in the real world of our universe, in that it's very difficult to source an infinite plane wave to go across the universe. You would basically need it's like a swimming pool, right? You'd need an infinite wall pushing to send it out. Yeah. Sorry? The black hole, like the Schwarzschild solution. I don't think so, because isn't there's an extra term here, right? These guys need an extra term. These guys need to have an extra term. I don't know. But maybe you can put Schwarzschild in this form. I don't think you can, but maybe you can. Like, probably you have to put it, it's a trivial, right? There's probably some trivial solution there. It has to be, so this is a requirement for it to be a solution to the vacuum Einstein equations, which Schwarzschild is. So maybe if you make, I don't know what would happen if you made one of these 0 and one of these a constant, but like Kung-won says, this cannot be 0 in that case. This is generically 0 if it looks like that. So it cannot, I don't think you can put Schwarzschild like this. But if you want to calculate, feel free to. I don't know, but I don't think so. Right. So, this now. Why are we interested in binaries? So, the things that we've observed so far with LIGO are systems of two objects going around each other. Right? That is not the only way of getting one of these changing quadrupole moments, right? You can have any non-symmetrical shape that is changing in some way. For example, my body, if I was spinning around, dancing, jumping around on the stage, I would also produce gravitational waves. Why binaries? The reason why binaries are interesting is because in a binary, this is the most efficient way of distributing your mass so that you produce the most gravitational waves with the given mass. So if you have all your mass in the middle and a little bump on it, and it goes round with a little bump, it will produce gravitational waves, but not very much. If you split your mass into 2 bits and stick them at 2 sides of your system and have them going around each other, even in a gravitationally bound system, for example, that is the most efficient way of maximizing this quadrupole and producing the most gravitational waves. So this is why the easiest things to see in gravitational waves are binary systems. These are the easiest things to see in gravitational waves. But as I said, when Einstein looked at this and he realized this, and he looked at what kind of energy would be emitted, he found that the energy emitted for all conceivable sources would be tiny. So me standing here dancing around the stage emit absolutely tiny amount of gravitational waves. And he came up with an equation like this in slightly modern units. There is a big number at the front, 10 to the 40, but then it is multiplied by a bunch of numbers that quickly make it very, very small. If you work it out, for example, the Earth going around the sun, and you put in the values here, the mass, the frequency of the Earth going around the sun is 1 per year. It's much more than 10 hertz. So this sort of thing, the frequency is much lower than 10 hertz. So this sort of thing suppresses this greatly. So the energy emitted, for example, by the Earth going around the sun is trivial. It's like a few joules. You have no chance of ever measuring it. It has no effect on the Earth's motion. There are many, many other things that are much more important for determining the Earth's motion around the sun than emission of gravitational waves. However, and what Einstein didn't know is if you put values in here where the mass is roughly the mass of the sun and the frequency that it goes around is roughly 10 hertz, then these factors here are roughly 1, and you get this huge factor out the front, 10 to the 40, and you get 10 to the 40 watts very, very easily. So if you can arrange for a system to have roughly the mass of the sun and it to go around in a binary at a rate that is faster than I can move my hands, right? You have to have more than the mass of the sun going around faster than I can move my hands, then you can produce huge amounts of energy in gravitational waves. So if you have a binary black hole system at around 100 hertz, going around 100 times a second, two black holes, mass of the sun, more than the mass of the sun, going around each other 100 times a second, they will produce 10 to the 47 watts of power in gravitational waves when they're doing that. Right? This is what we see with LIGO. 10 to the 47 watts is a huge amount of energy. Right? The total amount of energy, the electromagnetic luminosity of the sun is 10 to the 26 watts. There are some 10 billion, 100 billion stars in the Milky Way. So the total electromagnetic luminosity of the Milky Way, 10 to the 37 watts. And there are some 100 billion, trillion galaxies in the observable universe. So the EM luminosity of all the visible galaxies in all the universe that we can see is comparable to the amount of energy that is being emitted in gravitational waves by these systems that LIGO sees. Right? So Einstein's claim that this would emit trivial amounts of energy and never have any actual impact on the universe is totally wrong. Problem is he didn't know that you can have black holes, objects that are so small that they can go around each other very, very, very quickly. Right? Why is it so difficult to detect it? It produces a large amount of energy. But then it's, so for the binary or for the supernova?
So compared with the energy produced by a supernova, is it the same?
No, this is much, much more than the energy produced by a supernova. Much more than.
Supernova is so visible. Why?
Yes. So the reason why is because a supernova is producing that energy in photons. And photons have a very strong coupling with all the stuff we have here on Earth. The gravitational waves couple very weakly to stuff here on Earth. And so it's actually very, very difficult to measure them.
But in terms of energy.
But the energy that's being produced, well, the luminosity that's being produced.
Observed on the Earth, actually.
Yes.
The energy. Observe the energy.
Yes, the energy that's fluxing through the Earth is much larger in gravitational waves than it would be for a supernova at the same distance. Yes. Yes. It is. And the cumulative energy that is emitted is also much larger. So these binary systems that are seen by LIGO, they emit about 5% of their total rest mass energy in about 1/10 of a second. That's like 3 solar masses of energy being emitted in 1/10 of a second into gravitational waves. And it then propagates out in all directions in the universe and finally gets to Earth, and some of it fluxes through the Earth, but it interacts very weakly with the detectors.
But the question is, the right way to ask the question is, how much energy, gravitational wave energy, will be transferred to the Earth?
Mm-hmm.
Or some object passes.
Mm-hmm.
So that's much smaller than the electromagnetic wave case. Why? Because of the meeting question.
The transferred energy is, but the energy that's fluxing through is much larger.
Much larger? But
Yes. So it's going like r squared, the size of a sphere, whatever distance you are from the source.
But physical effect on the passing object
Yeah.
is very
Yeah, it is. Or the interaction, yes. Yes, it is. That's why it's so difficult, yes. And that is because the coupling of gravity is very weak compared to the coupling of electromagnetism.
Gravitational energy is much more than the supernova, energy from supernova is mainly from nuclear reaction. But it's gravitational reaction.
Yeah, in a very general sense, yes, you could say that. Yes. I mean, it does depend on how everything is set up, right? So the fact that you have a binary of two stars going around each other is not quite the same as the nuclear processes that are causing the supernova, and the energy per nucleon involved in some interaction could be different, but broadly speaking, that system, yes, the energy is the gravitational waves, and gravity is much more efficient at extracting energy out of that system than nuclear is, yes. But it's very inefficient when those black holes are far away from each other. So even if they're the distance apart that the Earth is from the Sun, gravitational waves would be very inefficient, right? Because then the frequency would be very low in here, and this would just get suppressed massively. Right. Little note about quantization. So we have gravitational waves, and we know from quantum theory if we have waves, they should be quantized, and there should be particles associated with those gravitational waves. But gravitational waves are a classical prediction of classical gravity, of classical Einstein relativistic gravity. If you believe that there is a quantum theory of gravity, then the quanta that you would associate with gravitational waves are gravitons. And we call them gravitons. Right? So these would be the quantum particles associated with gravitational waves. If you try to work out how many gravitons there are in the gravitational waves that LIGO sees, you will find that there are lots and lots and lots of gravitons, many, many, many gravitons. Right? You're not detecting individual gravitons with LIGO, you're detecting huge coherent states of vast numbers of gravitons. And this is a quote from Felix Pirani, who was one of the people who came up, who sort of put the theory of gravitational waves on a firm theoretical footing. And he said the primary motivation, this was back in the 1960s when one of Kung-won's periods of great progress in gravity was occurring. The primary motivation for the study of gravitational radiation, i.e. gravitational waves, is to prepare for quantization of the gravitational field. The reason why people were studying gravitational waves in the 1960s was not because they were thinking of LIGO, not because they were thinking of binary systems and mergers of black holes. It was because they wanted to understand radiation in gravity so that they could then quantize it, and quantize it as gravitons, spin two particles with their interactions. Now, I said that if I dance here on the stage and wave my hands around, I will emit gravitational waves. By the way, are one of you keeping a track of the time?
Yeah, you have 15 minutes.
15? Right. Okay, just stop me when you've had enough, right? So, if I stand here and I wave my hands around on the stage, according to Einstein's theory, classical theory, I should emit gravitons. Right? Not very many. I won't emit very much energy, but I will emit some gravitons. And if you use this formula here for the power, so my hands here are roughly about 1 kilogram in weight. They are about 1 meter from my body. I move them up and down at like frequency of about 1 hertz, roughly like this. Then you can work out what power output I should put out, and that is 10 to the minus 54 watts. It's absolutely tiny. Right? The frequency that I'm emitting gravitational waves, the gravitational wave frequency is 1 hertz, because that's the frequency at which I'm waving my hands. And so the energy of each of the gravitons that I produce is 10 to the minus 34 joules. And if you want to have a power output of 10 to the minus 54 watts with particles that have 10 to the minus 34 joules each, you see that you produce about 1 graviton every 10 to the 21 seconds. Right? So as I stand here and wave my hands around, I will produce 1 graviton in every 10 to the 21 seconds. 1 graviton, it will take me many, many times the age of the universe before I produce 1 graviton, or I have a good probability of producing 1 graviton. Right? Yes?
How you estimated that energy?
Which, this one? This is HF. This is HF with F equals 1 Hertz.
Do you think that that formula is applicable
Yes.
to graviton?
Yes. They are massless particles. Yes.
I'm not sure if that's true.
So,
Otherwise,
at what level are you not sure it's true? Are you not sure it's true at the level of, eventually if I keep asking questions about this, I will find some contradiction because I have quantized gravity? Or are you not sure that I can just say I have a massless spin 2 particle, what is its energy? It's HF.
You can put that actually can evaluate from just gravitational wave radiation.
Yeah.
well, I don't think that formula is applicable because if that's applicable, then we have the gravitational wave
Yep.
at the frequency of 100 hertz
Yep.
or larger,
Yep.
and then probably it's
Yep.
like the photon.
Yep.
So it should have some effect.
Yep.
And the nature of gravitational wave is
Yep.
lost, missed, and it's just quantum.
Yeah, 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 yeah,
So
yeah.
you should see some effect.
Yes.
But
So what? You should see an effect of a individual graviton. If you calculate how many gravitons it is that's fluxing through the LIGO detector when it sees an event, it's lots, 10 to the 20 or something. It's a lot.
It's a lot.
It's a lot. So you're seeing a coherent state. You're not seeing individual quanta.
Okay.
You're seeing a very, very coherent state. You're not able to discern the popcorn of individual gravitons. There's no photoelectric effect.
Okay, go ahead.
So anyway, this calculation here, which is very, very rough, admittedly, is my justification for why waving my hands is a quantum gravity experiment. Right? Classically, I should be emitting gravitational waves. Quantum mechanically, I'm only doing that once every 10 to the 21 seconds, once every many times the age of the universe. So every time somebody asks a string theorist, what experiment can you do that is a quantum gravity experiment, and they wave their hands, that is a quantum gravity experiment right there. Right, so this then comes into the issue of, which is maybe what Kung-won is getting at, is what is the energy of gravitational wave? Right? This is one of the things that even after Einstein's death in 1955, people argued and argued and argued about whether gravitational waves, you can write them down, you can write down a metric for them, but do they carry energy? And if you do this linearization procedure, write this linear perturbation down and drop it in the Einstein equations and throw away everything that's h squared, what you will do when you do that is you will throw away any ability of those gravitational waves to carry energy, because they do not carry energy at the linear order. So the thing that all the PhD students write down in their thesis, they are gravitational waves that carry no energy. This argument of how do we know whether these things carry energy or not is a complicated argument in perturbation theory, because you need to go to second order in the perturbations in order to see that they're carrying energy, and then you have to do the propagation equations at second order, and then you have to go to third order in order to get the energy correct, and you keep going, and it's a bit of a mess. Right? So this issue of do they carry energy was something that the theorists argued about a lot in the 60s and 70s. The way that a lot of people do, the approach that a lot of people take to calculating the energy of the gravitational field, this is what Einstein did. This is what is in the Landau and Lifshitz textbook in 1951, is you calculate what is called an energy pseudotensor. So you associate a pseudotensor with the energy of the gravitational field. Right? So there is an effective energy momentum tensor here associated with some derivatives of the metric. Now the reason why this is a pseudotensor is because if you change coordinates, it will change its value. So it can be 0 in some coordinate systems and not 0 in other coordinate systems. it is a pseudo-tensor, and one has to be very careful how you treat the coordinates when you do this, right? It can be done, but you need to be very careful. And it's kind of against the thing that they teach you in general relativity, which is you should treat everything as tensors. Right? This is an effective energy momentum tensor of the energy in gravitational waves. So you have your background, and then you have something on top of it, and it will act as an effective source for curvature. This too? So this one, this Isaacson tensor, this is 1968, this is actually a tensor, or it's actually it's a tensor that you can define as a tensor, and you can change the coordinates and it will keep its value. What has to happen is you have to have these angle brackets on, you have to average it over some region. So you have to write down what your metric is over some region, take its covariant derivative, do this contraction, and then average over some region to turn it into a tensor for a point. So it has knowledge about non-local extent. Right? This you should probably fix a gauge here in this. You should fix the gauge in a covariant way. As long as you're fixing the gauge in a covariant way, this will be all right. So you can project out the non-physical degrees, but you can do it in a covariant way. So it took until the 1960s, this was the topic of big discussion, before people started to get comfortable with the idea that these gravitational waves could actually carry energy. Because at the when you do this linearization perturbation stuff, it leads to a giant mess. It was only when people started understanding these kind of things that they started understanding that gravitational waves really do carry energy and can take energy away from a system, such that if I have two objects orbiting around each other, energy will be taken out of the system and the objects will get closer and there will actually be an effect. It's not just some weird coordinate effect on the gravitational field. Yeah, this is the general metric.
If you apply the linear theory, then you will get the bottom bubble.
So they will be consistent with each other in some cases, but they will not be consistent with each other in other cases. This one up here, this one can lead to all kinds of problems in certain spaces. So you can make this non-zero in flat space. Right? This one, as long as you do the averaging carefully, it will be zero in flat space and not zero in a gravitational wave space. So if you drop that PP wave into here, you will get an energy associated with it. So the gravitational waves, they carry energy momentum, they carry energy. It is just space-time, it is just the metric, right? There is no matter. They carry energy momentum, but unlike other fields, you cannot localize this to a point. You cannot say the energy in a vacuum space-time at this point is so many joules. There is no pointing vector for the gravitational field. And this is because of the equivalence principle. At a point, you cannot tell whether you have a gravitational field or not. Yes?
So are both of them conserved in usual space?
Yes, they are. In fact, this one comes from precisely that kind of conservation requirement. That's exactly how you derive it. Yeah. But the covariant derivative will be zero. Or the pseudo covariant derivative will be zero. Yeah, that's exactly how you derive it, actually. You basically integrate up that conservation equation. So you require that whatever this is, it's something that is conserved for the covariant conservation, and then you basically back this out of it. Right, so the gravitational waves, they carry energy, but you cannot put it at a point, you have to average it somehow. This is just the way that gravity works. You cannot, there is no local definition of energy in gravity. Now I come to this, and maybe this will be the last thing I'll talk about. So this is now what is known as the Bondi-Metzner-Sachs metric. This is also from the 1960s. What people were trying to do was trying to, again, understand what are gravitational waves and put them on a rigorous mathematical basis. And these guys, what they were looking at was not exact solutions, but they were looking at the asymptotic properties of some spacetime. So you have some spacetime, and at asymptotic regions far away, you have some structure in the asymptotic region that where the source terms disappear and everything falls off suitably well so that it's asymptotically flat. So spacetimes that are asymptotically flat. So you have some black hole in the middle, it does its thing, but if you get far enough away from the black hole, you asymptotically go to a flat space. And they were looking at the symmetries that are possible in those asymptotically flat regions. And they wrote down this very general metric for any spacetime that is asymptotically flat. So there are all these kind of functions in here. You'll see all these functions. These are all free functions that you can determine by your specific solution. But whatever your solution is, if it's asymptotically flat, it can be put in this form. And then in particular, there is this metric function here, this CZZ here, that defines a thing called the Bondi-News function by its partial derivative with respect to the coordinate u. This thing here, Bondi-News function. And if that Bondi-News function is non-zero, then you will have flux of gravitational waves through infinity. So this is a fully general statement of whether or not you have gravitational waves at infinity, far away from your sources, whatever your sources are doing. You don't need a full solution. You don't need to work out exactly what the sources are doing. But at infinity, this will tell you, the news function will tell you whether there are gravitational waves or not. And in addition, because it's asymptotically flat, you can define a notion of energy. And the energy flux at infinity is going like the square of this Bondi-News function. So at this point, this was the point at which people were starting to put together the mathematical structure to define in a precise way what it meant to be a gravitational wave, beyond all this linearization stuff. Now this Bondi-Metzner-Sachs business, this space-time, it's a structure at asymptotic infinity. Actually, it's asymptotic null infinity. It's where you end up if you go at the speed of light to infinity. Travel at the speed of light to infinity, you end up at asymptotic null infinity. This spacetime has a structure of symmetries. Those symmetries are described by a group. That group, unsurprisingly, is called the Bondi-Metzner-Sachs group. It describes the symmetries at asymptotic null infinity. And it has some very curious properties that are related to gravitational waves. First of all, that group is much, much larger than the group of symmetries that describe flat space. So if you have Minkowski space, there is a Poincare group that describes its symmetries. It's finite dimensional. This Bondi-Metzner-Sachs group, which describes the symmetries of asymptotically flat spacetimes, is infinite dimensional. It's infinitely bigger than the group of symmetries that describe flat space. And also, it has some rather curious properties that describe how gravitational waves can cause permanent deformations to flat space. If you have a gravitational wave that propagates through flat space, it can permanently deform flat space. So it takes flat space from flat space to flat space, but flat space with a difference. Somehow the flat spaces are different, and it is described by this BMS group. I'm going to talk about that in great detail, but that is what is known as the gravitational memory effect. And people in LIGO are very excited and hoping that they might, if they're very lucky, be able to observe this gravitational memory effect. And people like Stephen Hawking have written papers suggesting that this gravitational memory effect may have something to do with black hole information. I am not going to talk about that, I just mention it in passing.
So, what is
MB. This is the Bondi mass. This is known as Bondi mass. Yeah. And yeah, it's related to this flux. So the Bondi mass is changing when you have that flux. When there is a flux, that Bondi mass will change.
So here, all functions should be real or flat?
So they're all real. All these functions are real. It's a real metric. Yeah. And that Bondi mass, you can map it onto the ADM mass at asymptotic spatial infinity. So it kind of plays a role similar to the ADM mass, such that if you have a flux of gravitational waves, it can change your ADM mass from one value to another value, and the difference will be that Bondi mass. Okay, so that is the end of me talking about the theory. This now is, and I will stop here, I'll just mention this. This is now the first observational evidence for gravitational waves that was made by these two gentlemen, Hulse and Taylor, using the Arecibo telescope in Puerto Rico, where they were able to track two pulsars going around each other and see that they were emitting energy, and that energy exactly matched the prediction for how much energy should be emitted by gravitational waves. Right? And that is this plot here. It shows that, and they won the Nobel Prize in 1993. So they made this discovery in 1974, basically showed that gravitational waves did exist in nature, and they won the Nobel Prize in 1993. They did not see the gravitational waves directly, but they saw its indirect effects on the binary system. The binary was getting closer together because it was emitting gravitational waves and losing energy. So it shows that when Einstein said gravitational waves would have no practical effects, they were wrong already in 1974. Okay, I'm going to stop there, and then we will pick up this on Wednesday. How far are we from the end? Oof, quite a way. There.
Why Einstein thought that there is no gravitational wave?
So there were several reasons. So you want to repeat the question for the microphone?
So why Einstein thought that there is no gravitational wave?
So there are several reasons. He changed his mind about this several times. The very first time that he thought there were no gravitational waves was because he was looking for the exact analogy of electromagnetic waves, and he was looking for the effect of a dipole, changing dipole, producing waves. Yeah, and he found that couldn't happen. The reason why he thought there were no gravitational waves in the 1930s was because he was looking for an exact solution for the full nonlinear equations to describe gravitational waves, and he found that he was unable to write one down without there being an infinity somewhere there had to be a singularity. And because he thought that singularities were unphysical, he decided that all exact solutions that have singularities in them are unphysical, and he thought that he had a proof that you couldn't do it without singularities. And it was that the referee showed was wrong. Yeah, and he was not even, he didn't even participate in this argument about whether they carried energy or whether they could be produced by objects that weren't accelerating. So in electromagnetism, you know that you have to accelerate a charge in order to produce electromagnetic radiation. In gravity, if the only force you have is gravity, the particles don't accelerate. They're just freely falling. They're following geodesics. Then you might worry they're not accelerating, so then there should be no gravitational waves. I can accelerate them by wiggling them with my hand, but if they're just freely falling under gravity, there would be no gravity. So There are a number of reasons why people, in addition to Einstein, were confused about this. It took a long time to figure out all the questions.